very great pleasure for me to introduce Randy Grace this afternoon for our tutorial on modeling and quantitative methods. Randy took his undergraduate degree at MIT, graduating in 1983 in electrical engineering. He worked with computers, both hardware and software, for several years, and then wound up at the University of New Hampshire studying psychology, where about a year after entering New Hampshire, he encountered the experimental analysis of behavior in a seminar. And all of a sudden, there were these piles of beautiful, orderly data generated in a variety of experiments accumulated over the past several decades. He looked at that, numbers, beautiful data, order, how to approach it. I think his approach could fairly be said to try to write a descriptive model for as much as he could possibly encompass, pursue the implications of that descriptive model, try to devise experimental tests to see if the model was plausible, and move on, keep on finding a new problem defined by the order in the data and the model that described them. The modeling is an integral part of the process. Randy has pursued it very effectively, and he's now going to try to give us some insights into how to get going on that kind of process ourselves. Sir, it's been a pleasure to be your friend and your colleague.
Oh, thank you. Thank you. I think Tony really should be the one giving this tutorial on quantification, but you're stuck with me for the next hour, so here we go. So, my topic is quantification, and that means numbers. What do we do with numbers? After you've collected data in your experiment, where do you go from there? And so really, the general question that we're trying to ask is, how do we go from numbers to meaningful statements about behavior? And of course, this is really what our science is all about. And I will give you a very general answer that we make decisions, that quantification and data analysis is all about making decisions about data. Now, I have to be honest, this is a tutorial about statistics. If that means you're going to leave, go ahead and leave now, and please be quiet. But hopefully, it won't be too painful. And really, we need to talk about statistics because statistics is meant to be a framework for making rational decisions about data. Now, I put a question mark on the transparency because, as probably most of you know, the practice of statistics, in particular null hypothesis testing, has been controversial among behavior analysts for quite some time, and recently has been controversial in mainstream psychology. And one of my goals today is to review some of the reasons why the use of null hypothesis testing and inferential statistics has become so controversial, but also to perhaps give you another way of looking at it, another way of looking at the practice of hypothesis testing that might be more consistent with what we as behavior analysts have been doing for the last 40, 50 years. So, that's the goal. And I thought I would start with, because I teach a stats course now, I always like doing this. Let's just have a little quiz at the beginning of the tutorial. And don't worry, this is an easy quiz. The questions are all true, false. If my students got a test that was all true, false, they would love me. So here we go. Suppose you have a drug that you suspect may alter performance on a memory task. You compare the means of your control and experimental groups with 20 rats in each group. Use an independent means t-test, and your result is t equals 2.9 on 18 degrees of freedom with an obtained p-value of 0.01. Please mark each of the following statements as true or false. Okay, so the first question. You have found the probability of the null hypothesis being true. Okay, so think, is that true or false? Second question. You can deduce the probability of the alternative hypothesis being true. Okay, straightforward so far. Third question. You know, if you decided to reject the null hypothesis, the probability that you're making a wrong decision. And fourth question, you have a reliable experimental finding in the sense that, hypothetically, the experiment were repeated a great number of times, you would obtain a significant result on 99% of occasions. And we can assume for the purposes of this quiz that the significance level decided on in advance was 0.01. Okay, well, hopefully you've got your answers to that quiz. Decided on your answers. This quiz was actually put to a panel of academic psychologists, that is, people with PhDs and teaching stats courses and so on and so forth, by Michael Oakes back in 1986. And here are his results. I think there were about 70 of them in the sample. And shown are the percentage of true responses. Now, in fact, each of these statements is false. But let's take each one in turn. You found the probability of the null hypothesis being true. Well, 35.7% of the sample agreed with that statement. They were probably thinking that the obtained p-value, p equals 0.01, that was the probability of the null hypothesis being true. In fact, that's false. The second one, you can deduce the probability of the alternative hypothesis being true. 65.7% said that was true. Now, I don't understand how. It seems to me that 1 and 2, like 2 is the converse of 1. That if you find the probability of the null being true, that's 1 minus the probability of the alternative hypothesis being true. But yet, 65.7% said that this was true. This is also false for the same reason that number 1 is false. The reason that both of these are false is because the obtained p-value that you get in a null hypothesis test is a conditional probability of data, of obtaining some data, given that a hypothesis is true, given that, for example, the null hypothesis is true. That's what the p equals 0.01 means. It is not the conditional probability of a hypothesis being true, given that you've collected data. Those are two very different things. From a frequentist interpretation of probability, the first conditional probability, this is a meaningful statement, but a probability of a hypothesis being true or false, that's a statement of degree of belief. And that is a no-no. That is like the worst sin to commit if you're a statistician, because a hypothesis is either true or false. You can't meaningfully talk about a degree of belief. Okay, third question. You know, if you decided to reject the null, the probability that you're making the wrong decision, well, our sample of academic psychologists was quite confident on this one. 85.7% said it was true. In fact, this is also false. Why is this false? Well, most likely they thought that the significance level was the probability of making the wrong decision, but the significance level is the probability of making a type 1 error, of falsely rejecting a null hypothesis that's true. It is not the probability of making a wrong decision. Why is that? Because what if the null hypothesis really is false? Then the only mistake that you can make is failing to reject it, and that's a type 2 error. And so we don't really know the probability that we're making a wrong decision, because we only know the probability of making a type 1 error if the null is true. So question 3 is also false. And finally, you have a reliable experimental finding in the sense that if it were repeated a great number of times, you would obtain a significant result on 99% of occasions. Well, this is a confusion of significance level with replicability. That if you have a significant result, that means if you repeat the experiment, you should also get the same result. You should also reject the null hypothesis. Now, if we go back to the statement of the problem, Michael Oakes was very crafty. You'll notice that the obtained p-value was exactly equal to 0.01. If the significance level were 1%, then if you had to guess what's the probability that an exact replication would reject the null hypothesis at the 1% level, you would have to say that it's 50%. Why? Because if you got a result that was either less extreme or more, you have no reason to expect that the result is going to be either more or less extreme than the one that they obtained. And if it's less extreme, because you're sitting right on that cusp, right on that 0.01 level, you would fail to reject the null. So without knowing what the effect size is for the experiment, you can't say anything about the probability that a replication would produce a significant result. So there are a number of confusions here about hypothesis testing, and they've been summarized in a number of articles by Jacob Cohen and other folks. Perhaps the most pervasive is the confusion of the significance level with the probability of the null hypothesis being true, and that's the one that I alluded to earlier. The confusion of the significance level with the replicability of the experiment, and also the confusion of the significance level with effect size, so that the smaller the obtained p-value, the larger the effect, or the more important the results must be. And all of these are fallacies. Well, okay. Some might say, all right, it might be a little bit confusing to understand null hypothesis testing, but surely there are some great virtues. For example, doesn't it control our type 1 error rates? So that if you look at a research literature in psychology, and look at all of the published studies in that area, shouldn't on average only 5% be wrong? Are there only going to be 5% type 1 errors? Well, in fact, this is not necessarily true. And consider the following contingency table. This is due to a fellow by the name of Pollard. Let's assume we have 5,000 hypothetical experiments in which the null hypothesis is true 80% of the time, and in which a typical study has 50% power. In other words, the probability of a study getting a significant result if the null hypothesis is false is 50%. And that's consistent with several analyses of power of studies in psychological research. Now, if you do a little 2x2 contingency table, you find that the null hypothesis is going to be true 80%, or 4,000 out of the 5,000 times. So that's the first column. And there will be just, if you use a 5% level for your null hypothesis test, that will give you 200 type 1 errors. Now, for the 1,000 experiments, that is the 20%, for which the null hypothesis is actually false, we've only got a power of 50%. So that means we will have only 500 rejections and 500, of course, type 2 errors. Now, if we assume that all rejections of the null hypothesis get published, then that means we're talking about 700 articles, and of those, 29% will actually be type 1 errors. So sometimes proponents of null hypothesis testing say, well, at least we know what the type 1 error rate must be. In fact, we don't, because to know the type 1 error rate, you've got to know the base rate, how often the null hypothesis is true. And in fact, in general, we don't know that. So more confusions about statistics. Now, because of these confusions and others, the APA convened a task force which finally delivered a report a few years ago, and they backed away from an outright ban on null hypothesis testing and suggested instead that when it was used that it be augmented with effect sizes and confidence intervals. But even confidence intervals can be a little bit confusing. So here's the extra credit question for our stats quiz. Here we have a 95% confidence interval for a mean difference. It does not include 0. It goes from 2 to 8. And the question is, what does this 95% confidence interval mean? And this is a multiple choice, A, B, or C. A, there's a 95% chance that the true population mean lies within the interval. When I ask students, this is the one they most likely want to choose. B, 95% of all replications of the experiment will produce sample means that lie within the interval. Seems like a reasonable statement. Or C, none of the above. Well, anytime you have a multiple choice question and there's none of the above, it's probably going to be that. In fact, the correct interpretation of a 95% confidence interval is, given an infinite number of replications of the experiment, 95% of the intervals that you construct according to that rule will contain the population mean. It's not the same statement as saying that there's 95% chance that the population mean lies within the interval. This is the same confusion of the conditional probability of a hypothesis being true with the conditional probability of obtaining data, given that a hypothesis is true. So even confidence intervals, despite their great virtues, can be pretty confusing. So if we sort of step back from all this and try to reach some kind of a verdict on the practice of statistics within psychology, well, collectively, I mean, we as the field of psychology, we wanted a rational framework for making decisions about data, but instead we just became more confused. That's what's happened. So what can we do? And we could abandon the use of stats in favor of single case designs, but that's what a lot of us do in behavior analysis, or other people, lots of folks have been arguing that we should abandon hypothesis testing and use confidence intervals and meta-analysis. And both of these alternatives solve some problems, but introduce new ones on their own. So for example, when you use single case designs, you still have to face the question of generalizing your results from the experiment of the species that you're studying beyond to other environments, other contexts. With confidence intervals and meta-analysis, well, meta-analysis, I think, has been sort of trumpeted as a panacea by many people, and I don't have time to spend really much really go into meta-analysis in any great detail, but I'll just say that the problems of low power and confusion about what a null hypothesis test means and so forth are effectively bumped in meta-analysis from the level of the single study to the meta-analysis itself. Because when you do a meta-analysis, you're looking, sort of surveying an entire domain of studies, and you're doing moderator variable analyses. You're looking at which variables predict differences in effect size. And you're still doing hypothesis testing, so it's susceptible to all the same confusions. And most importantly, neither of these tactics, neither adoption of single case designs or meta-analysis, really saves us from responsibility of having to make decisions about our data. I mean, that's the bottom line. We still are responsible for making decisions, and nothing will stop us from making the wrong ones. So what I'd like to do now is just try to collectively forget everything that we know about stats, everything that we know about data analysis, and what if we had to start again? You know, what if we had to figure out all by ourselves how to analyze a set of data? What would we do? And as one possible example, I'd like to present a case study about a graduate student named Fred. Now, Fred is a graduate student who had a series of 10 insights over one weekend. He's smart, works hard, and is good at mechanical tinkering. He used his mechanical ability while he was a graduate student to construct a radial arm maze. And I don't know if it comes out very well, but you can see his radial arm maze, and there's a little rat in the first arm. Fred did an experiment, his first experiment as a graduate student, in which he was looking at the effect of type of chocolate, either Hershey or Cadbury, on rats' performance in a radial arm maze. Now, it's time for Fred to analyze his data because on Monday he has to present his results at the conference for graduate students in his department, and whether or not he gets an assistantship for next year rides upon the quality of his talk. But, unfortunately for Fred, he disliked his statistics course and has forgotten all that he knew, and the library is closed, so he has no resources other than his own head on which to rely, and he's got to analyze his data. So, okay, here are Fred's data. These are the mean number, or rather the number of correct choices made by the rats in each of the two groups, and correct choices would be, in a radial arm maze, the number of different arms that the rat visited until it went back to one that it had already been to. And of course, each arm is baited with a piece of either Hershey or Cadbury chocolate. Now, Fred looks at his numbers for a while and realizes he's not getting anywhere. And he's always been a believer in graphing data, making pictures, and so he makes a simple graph of his data. Just like that. And the data for the Hershey group are shown in the filled squares, and the data for the Cadbury group are shown in the unfilled squares. And as Fred is looking at his data, he has his first insight. There is variability. Not all the rats do the same thing, even if they get the same chocolate. Well, that's clear. The points are kind of scattered around. And hot on the heels of that first insight, he has his second, which is that chocolate might have an effect, although it's uncertain. If you look at the data, it looks as though the Cadbury group is doing slightly better. Most of the points are higher in the Cadbury group than in the Hershey group, but there's 1 point in the one rat in the Hershey group that had more correct choices than one rat in the Cadbury group, so perhaps it's not entirely clear. So it looks like chocolate might have an effect, but it's uncertain. And as Fred ponders this insight, he realizes that he's going to have to make a decision. He's going to have to reach a conclusion about the results of his experiment. And there are two possibilities. Either chocolate has an effect or it doesn't. But he knows that he needs to somehow make these different possibilities more specific. And he then has his third insight, which is that there's a way to make the possibilities explicit by combining the first two insights that he's had, namely that variability and the effect of chocolate combine in an additive way. Now this might be a time when I could leave this up over here. In other words, we can assume that the performance of each rat, the number of correct choices, is some effect of chocolate plus variability, whatever caused the rat to behave the way it did in a way that was different from the other rats. And once we make that assumption, we can make the two possibilities a little bit more specific. So for example, if the type of chocolate matters, we're going to call this case 1. Fred's now thinking about case 1 and case 2. Case 1 just says type of chocolate matters. And so for the first group, the group that got Hershey chocolate, the number of correct choices should equal the effect of Hershey plus variability. And for the second group, the group that got Cadbury, the number of correct choices is the effect of Cadbury plus variability. That's the first possibility. That's the first case if type of chocolate matters. But there's the second case is that type of chocolate doesn't matter. And then the number of correct choices should equal just an effect of chocolate, which would be true for both groups. It would be the same effect for both groups, both Hershey and Cadbury, plus variability. Fred thinks about this some more and realizes that that's not really taking him far enough. It's not helping him to make choices between his cases because he's not bringing them into contact with his data. He needs to bring them into contact with his data somehow, and that's when he has his fourth insight, which is that the cases can be used to make predictions. This is actually a very, very deep insight that Fred has had. The cases can be used to make predictions. So for instance, what we can do is say, well, assuming that a given case is true, either case 1 or case 2, we can ask what's the most likely score for rats in a particular group to get, given that that case is true. Now, how do we make our prediction? Well, perhaps the best way to make a prediction, our best guess as to what the rats are going to do, is simply to use the average. So for instance, if the type of chocolate matters, then for the rats in the Hershey group, we can use the average number of correct choices, 4, as our best guess of the score that each of those rats should be obtaining. And for the rats in the Cadbury group, we can use the average of that group, which is 7, as our best guess, as our best prediction of what a rat given Cadbury, how many correct choices are they going to make. Now that's for case 1. For case 2, type of chocolate doesn't matter. And here, what we can do is just use the overall average of all 10 rats and use that as our prediction. That would be our best guess for how many correct choices any given rat would make. The average is 5.5. So now Fred is starting to feel pretty confident. He's made some progress. He's got the cases that he has to decide between really stated in a pretty specific way, and he's brought them into contact with his data by making predictions. Of course, Fred is a little bit puzzled about the predictions because there seems to be something a little bit circular with using the data to make predictions about the data. And so maybe there's a sense in which, instead of making predictions, the cases are really being used to describe the data. That is, this is the best description that we have of the data, given that case 1 is true. We have a different prediction for each of the two groups, and our best description of the data, if chocolate doesn't matter, is simply to use the same prediction for all groups. Fred then has his next insight, which is that to make his decision, he's going to have to compare the two possible cases, and that means assessing or measuring how good the predictions are. He's got to have a way of measuring the predictions of each of his cases. And the simplest way to do that, it seems to Fred, is simply to look at the difference between the number of correct choices that the rat made and the number that was predicted. So for instance, for the first rat in the Hershey group, there were a total of 3 correct choices, and we predicted 4. So that little blue line is the obtained minus predicted, which is a kind of discrepancy or error score. And what Fred really wants to do is know how accurate the predictions are for each of his groups. But if he figures out a way to measure error or discrepancy, that's essentially the same thing, because error and accuracy are just two ends of the same scale. So if he wants to have the most accurate case, if he wants to pick out the most accurate case, it's finding the one that makes the least errors. And so Fred thinks, okay, well, I'll just go and look at the obtained minus predicted for each of my rats in both groups. And that looks like it's going to work pretty well, but then he realizes that some of them are going to be positive and some are going to be negative. And the positives and negatives are going to tend to cancel each other out. Now, Fred remembers a little bit of his math and knows that one way to get rid of a negative sign is to square something. So if you have -1 and square it, you get +1. So what he's going to do to prevent the errors from canceling out, because what he wants to do is come up with an overall error score for his cases, he's going to have to square the errors before he adds them up. And now Fred is becoming very confident, and he sets to work with his raw data and works out these squared error scores for each of the cases. So for instance, here's the first rat in the Hershey group, the score of 3, a prediction of 4 for case 1, an error that's obtained minus predicted of -1, a squared error of 1, and doing that for all the rats, given the predictions of case 1, we wind up with a sum of squared error of 20, and for case 2, that's the type of chocolate doesn't matter, and so we're always predicting 5.5, which is the overall average. We get the sum of squared error to be 42.5. So Fred is feeling really good now, thinks, aha, I'm making much less error with case 1 than I am with case 2. It's less than half. Doesn't that mean that I can go ahead and stop now and say that it's case 1 rather than case 2, and that chocolate really does matter? But then Fred has an uneasy feeling. because as he thinks about it, he realizes that this isn't really a fair comparison. That actually, case 1, in which you're allowed a different prediction for each of the two groups, is always going to have less error than case 2. Why? Because it's more complicated. Case 1 is really a special case of, or rather, case 2 is really just a special case of case 1, in that if you made the averages for the Hershey and the Cadbury group, if you made the predictions the same, then case 1 would be the same as case 2. So the fact that case 1 is more complicated means that it's going to have less error. And so Fred has his 6th insight, which is a fairly deep one, which is that there's a trade-off between the error that a case makes and its complexity. And he has this idea about freedom because how can we really talk about complexity? How can we really talk about complexity? And Fred thinks, okay, if we take this difference in complexity to an extreme, what if I had a really, really complicated case in which I was allowed to make different predictions for each rat, and I just made the predictions the same as the obtained scores? Fred realizes that, of course, that would be silly. I mean, that would be just a dumb thing to do. Why? Because there would be no way that the case could ever be wrong. There would be no way that the predictions could ever be wrong. And one way to ask, well, what's the effect of this complexity, is to say, well, okay, after I've made these predictions, how many of the data points are actually free to vary? And this is because of the problem of using the same data to make the predictions and then using those predictions to assess the same data. So for instance, if we are going to predict the mean of the Hershey group, then once we know 4 of the scores in the Hershey group, we can figure out what the last one has to be because we've already predicted what the mean is. And because that's also true for the Cadbury group, there are actually only 8 scores that are free to vary in case 1. And so Fred has his 7th insight, which is that we can measure freedom, and freedom is inversely related to the complexity of a case. We can measure this in terms of how many data points are free to vary after the predictions have been made. For instance, for case 2, we're only going to predict the same mean for both groups, and that says that 9 of those points are free to vary. If you specify 9 of them and you know the mean, then you can figure out what the last one is. So Fred is really feeling like he's reaching the home stretch here. Needs to think about a way to combine this notion of freedom with this notion of error that he'd already defined, but has another important insight as he's thinking specifically about his sum of squared error, where he's got 20 versus 42.5, and that is that error and freedom need to be measured in relative terms. Why is that? Because if you have a difference of 22.5, so 20 versus 42.5, that may be a large difference if the total amount of error is small. But if the sum of squared error was 1,000 and 1,022.5, it would be pretty small. So what we want to do is find a way to measure the difference in error and the difference in freedom between our two cases that's proportional. And what Fred realizes is that he can talk about a proportional increase in error. He can compare the error made in case 1 with the error made in case 2 by saying how much of an increase in error do you get going from case 1, the more complicated case, to case 2, relative to the amount of error that you make in the more complicated case. So that's just the error for case 2 minus the error for case 1 divided by the error for case 1. So that's expressing the difference between the error made in our two cases relative to the amount of error that we make in case 1. And similarly, we can talk about the increase in freedom in the data going from case 1 to case 2 by an analogous proportional increase in freedom measure, where we have the freedom in case 2 minus the freedom in case 1 divided by the freedom in case 1. And so Fred then, as he's thinking about these proportional increase in error and freedom scores, he has a very, very important insight, which is that the way to measure how good case 1 is compared with case 2, because remember that he had a problem. He can't just simply look at the difference in the error scores. He's got to take into account the increased complexity of case 1. But he can do that now by thinking about the proportional increase in error and the proportional increase in freedom as benefits and costs, respectively, of case 1 compared with case 2. In other words, the proportional increase in error is a measure of benefit. How good are we doing with case 1 versus case 2 in terms of reducing error? And the proportional increase in freedom is asking, well, really, how much of a cost in terms of complexity, how much added complexity do you have in case 1 versus case 2? So he's got his measures of benefit and cost, and his final insight is that he can make his decision by finding a benefit-cost ratio. He can simply look at the ratio of his benefits to his costs, and that can be the basis of his decision. And so Fred is really happy now because he can write the formula for his benefit-cost ratio. It's the proportional increase in error divided by the proportional increase in freedom, and it's that. And for his data, he can now just plug in the numbers to his formula. So he has 42.5 minus 20. That's the difference in error between case 2 and case 1, divided by the error in case 1, that's 20. And then the proportional increase in freedom is going to be 9 minus 8. So 9 is the freedom score for case 2, and 8 is the freedom score for case 1, divided by 8, the freedom score for case 1. And you work it out, and it comes to 9. And Fred is saying, aha, the benefits of case 1 are 9 times the cost of case 1. And so that seems big enough for me because it needs to be more than 1, right? For the benefits to outweigh the costs, that benefit-cost ratio needs to be bigger than 1. Now, how much bigger? Let's not worry about that. 9 seems big enough. And Fred is so happy with himself that he decides to commemorate his insights by naming his benefit-cost ratio rather immodestly after himself as F. And he takes it to his advisor on Monday, who pats him on the back and says, well, Fred, yes, you really should have paid attention in your statistics course because there's somebody named Fisher who's already called that formula F. And so you're just a little bit too late. What Fred has done is rediscover the analysis of variance. Now, that formula may not be the familiar form in which you encountered analysis of variance in your stats class. But if I rearrange it the following way, so starting with Fred's benefit-cost ratio, we can rearrange it and get the more traditional form of analysis of variance where we have a ratio of a between groups to a within groups estimate of population variance. And we ask, well, what does that F ratio or what does that benefit-cost ratio mean? If we consider the traditional interpretation of the F ratio, it goes something like this. We can form a pooled estimate of the population variance by examining the variation within each of our groups. A second estimate of the population variance may be obtained from the variability between the sample means. If the null hypothesis that all scores are sampled from the same population is true, then these estimates should not depart systematically from 1. However, if the alternative hypothesis is true, namely that the population means are different, then we expect the estimate based on variation among the sample means to be larger, and thus the ratio of the estimates should be greater than 1. As someone who's taught stats, this is what I try to get my students to understand, and they're often confused. Contrast that with Fred's interpretation of his benefit-cost ratio, which is simply, is the reduction in error in case 1 compared with case 2 enough to offset its greater complexity? Now, I don't know if you're like me, I think that Fred's interpretation of F seems a bit more intuitive, easier to understand than the traditional interpretation of F. And in fact, what Fred has done is to rediscover what's called the model comparison approach to analysis of variance. And he was of course talking about cases, case 1 versus case 2. But these are really models. These are different models of the world that Fred was creating, and then Fred knew that he needed to decide between. And it turns out that there is a very general form of F ratio which applies to basically any application of the general linear model, which basically casts a hypothesis test as a choice between what's called a restricted model or a simpler model, which is corresponding to the null hypothesis, and a full model or more complicated model, your alternative hypothesis. So for instance, in Fred's example, he was choosing between a model of the world in which the effect of chocolate was the same for both groups, Hershey and Cadbury. That was his restricted model. And a model of the world in which the effect of Hershey and Cadbury were different. And this is a very, very general approach. The standard reference for model comparison is the book by Maxwell and Delaney, but it's not very often taught. I think because, well, there aren't really very many good undergraduate books that use this model comparison approach. One important thing to recognize, I think, is that the third insight that Fred had, namely that the effect of chocolate and variability combined additively, that was kind of the heart of his model. That was how he started building his models. That was an application of essentially that equation, data equals model plus error, which is the fundamental insight, the fundamental equation, if you will, of exploratory data analysis, which was the method of data analysis pioneered by John Tukey. And I would say that probably most behavior analysts would feel quite comfortable with the methods and practice of exploratory data analysis. Tukey has contrasted EDA with hypothesis testing, which he calls confirmatory data analysis, by talking about the following characteristics. Instead of looking at sort of rigid tests of a priori hypotheses, exploratory data analysis wants to ask the question, what's going on here? We want to reach a substantive understanding of the data. We can use graphical representations of data and be very flexible in terms of the way that we might want to present the data. We use an iterative model, an iterative process of model building, analysis of the resulting errors, which are called residuals, and model respecification. I think that exploratory data analysis is really fundamentally similar, I think, to confirmatory data analysis if you accept a kind of model comparison approach. If you see hypothesis testing as really choosing between different models, then I think the dichotomy between exploratory and confirmatory data analysis vanishes. And because time is short, I won't be able to really talk about any other methods for model selection, but I'll just make a few general comments. A lot of what we do in behavior analysis or in quantitative analysis of behavior is coming up with models, trying to assess them, the methods that we use to assess them, looking at variance accounted for, analyzing residuals, the errors when we use the models to predict data, and finding out whether they're systematic, which implies that there's some structure in the data that the models have failed to capture. There are a whole host of techniques beyond the simple hypothesis testing in the general linear model, which is basically analysis of variance. You can use that for linear models. This is a way of choosing between different applications, different specific linear models, but beyond simply comparing variance accounted for, there are a whole host of methods that you can use for assessing the adequacy of models. And one method, which I've gotten into myself a little bit, is the Akaike information criterion. And this might look like a rather horrible equation, but actually it embodies the trade-off between error and model complexity that Fred was thinking about with respect to his rat data. Because the Akaike criterion has a term which basically represents goodness of fit, and a term which represents complexity in terms of the number of parameters that the model has, the number of different predictions that the model makes. And the Akaike criterion is very useful because you can compare different models that might have different numbers of free parameters, and the model that accounts for more variance might have more free parameters, and according to the Akaike criterion, the simpler model might turn out to be preferred. The AIC score, the Akaike score, you want to have a lower score, so that the lower the score, the better. And I think that methods like this will come to be increasingly used. There was a special issue in the Journal of Mathematical Psychology last year that was talking about a great number of these different methods for model selection. I don't think that a method like the Akaike criterion, or indeed any method of statistical model selection, will be a panacea for us, because I don't think that you can ever replace the judgment of the researcher. That is an essential element in data analysis. In Kazantzakis' last novel, which is about the Greek Civil War, there's a Father Yanoros, who has two sons, and one son is fighting with the communists. He's the rebel leader of the communists, and his other son is fighting with the monarchists. And there's a civil war going on, and brothers are killing brothers, and it's just a terrible scene. And Father Yanoros is a leader of his community, and the people are begging him to tell them what to do. What side should we follow? And Father Yanoros goes to his church and stays up all night praying to God to give him some insight, wants God to tell him what to do. And at 5 o'clock in the morning, he's been praying all night, fasting and everything. He finally has a vision of God. God comes to him. And he asks his question, what should I do, God? What should I do? Which side should I support? And he knows that God is going to speak to him and tell him this is the moment that he's been waiting for. And God says to him, I made you free. You decide. And I think there's a moral in that story for us as data analysts, that we are made free as researchers. And there is no statistical method which can take that responsibility away from us. We have to take responsibility for making decisions about our data. But fortunately, I think there are a great many quite usable and enormously flexible tools, very useful tools, like the Akaike criterion, like hypothesis testing, which can help us in that task. So thank you.
We have a few minutes for questions.
John.
I think this is what you're pointing out. It seems I have it right that standard statistical approach, which can be construed as model comparison, gives you the machinery that you need to compare models that
Yes, exactly right. Okay. What John is asking is one way to contrast model comparison with the Akaike criterion is to say that the model comparison gives us a way to make decisions, a way to choose between different models that are nested in the sense that they're both members of the same family. So in the sense that in Fred's example, case 1 was a special, or rather case 2 was a special case of case 1. It was just a difference of whether you had one mean or two means for your two groups. Those models were nested and in fact all of the hypotheses tests that you do with a general linear model are nested in that sense. And so it's got the trade-off between error and complexity built into the F ratio. The benefit-cost ratio is just built right in. With the Akaike criterion, the real flexibility of this is that you can take models that have nothing to do with each other mathematically. And the trade-off between error and complexity is built right into the AIC score itself. So you can calculate AIC for 7 or 8 different models and choose the one that has the lowest value. So, thank you. Yeah, Mark.
What would your suggestion be on what Fred does with his 9? How does he decide that his 9 is either going to be the basis of choosing Model 1 or Model 2?
Right. Well, I kind of finessed that one because Fred sort of recognized that he had his benefit-cost ratio and knew that if it was larger than 1 that he wanted to choose case 1. And it came out 9, and so Fred was happy because he didn't feel that he really had to make a decision. But if it had come out to be 2, I think Fred would have had to say, maybe I need to run some more rats.
I think at that point we're going to have to call it off. Thank you.